Thanks. Hey, everybody. So my name is Boudewijn Braams. I'm a software engineer at Databricks. I'm part of the storage and I/O team. And today I'm going to be talking to you about the Parquet format and performance optimization opportunities that it presents. So before we dive into the specifics, let's just take a step back and look at what we do when we do data processing and analytics. So we start off with a data source, be it a text file, a CSV file, XML, or JSON, Parquet, whatever. You feed it into a data processing or querying engine like Spark, and what you get in the end is like new insights, transformed data in the case of an ETL pipeline, or whatever. There's a lot of complexity in the data processing and querying engine. We won't be going into that that much, except maybe for the part of efficiently reading in the data. But we'll mostly be focusing on the data sources, of course, and specifically on Parquet. So a quick overview of the presentation. I'm going to be talking about data storage models in general, the Parquet format, of course, and the optimization opportunities that it presents. So let's take a broader look at data sources and formats first. So broadly speaking, you have this spectrum, right? Whereby you have unstructured data on the one hand, which gives you a lot of flexibility, but it has a really high parsing overhead. And on the other hand, you have structured formats, which are more efficient storage-wise, but also offer better performance. And let's give a description of these three categories. So you have the unstructured data. These are stuff like text files or just like raw text, not actually CSV. It should not be in that category, but it is for some reason. But in essence, there's no notion of a record, or there's no well-defined schema. So it's like it gives you a lot of flexibility. It's like it's super flexible, but it's really hard to parse. There's going to be a huge overhead there. Semi-structured data is a step in the right direction. In this case, these are things like XML files or CSV files or JSON files. In this case, you do not necessarily have a well-defined schema, but what you do have is a notion of a record or a row, which is kind of nice, and it improves the ease of parsing, and in this way speeds up your queries. On the other end, we have structured data formats, which is the most nice to work with. They're the fastest. They have the least parsing overhead and most efficient storage. You have both a notion of records and rows and a well-defined schema. What makes it performant is that you, of course, have very predictable locations for where each data element is going to be. And Parquet is one of these structured data formats. So how do you actually store a structured data format on disk? At the logical level, you always have this notion of a table, right? You have rows, and a row has columns. So how do you actually store this on disk? There's basically three ways in which this is done. There's the row-wise model, in which what you do, it's basically a one-to-one mapping of your logical model to the physical model, whereby you just store the column values of each row back to back. You have the columnar model, where what you do instead is you take all the column values of the first column, store these back to back, and do this for the second column and for the third column, and so forth. And there's, of course, there's also a hybrid model, which kind of combines these two models, where you have both horizontal partitioning of rows, and within that horizontal partition, you do vertical partitioning. But to analyze the performance of these different models, you have to, of course, recognize that there's different workloads and that they're going to behave differently under different workloads. So broadly speaking, there's two types of workloads. There's the traditional OLTP workload, which is online transaction processing. And what this is they're workloads with lots of small operations involving entire rows. Like, for example, lots of inserts or lots of deletes or update operations. The essence here, like what I'm trying to convey to you, is that these operations involve entire rows. OLTP is kind of our domain. Like it stands for online analytical processing, and the queries are very different. Like they are usually only a few very large queries operating on a subset of all the columns, so not the entire rows. Usually they're very large scans, and in the end result is a very small selection of the rows, and within that small selection of the rows, a small subset of the columns. The main assumption I have for the rest of this discussion is that I/O is expensive, like be it from memory or from disk or from the network. So let's look at these models in terms of, in the context of these different types of workloads. So first off, you have the row-wise model. Like I said, it's the most intuitive one. It's basically a one-to-one mapping of your logical model to the physical model. So if you have a row here with 3 columns, you map it on disk like this. It's very straightforward. It's very well suited for OLTP, as you can imagine, because you have, let's say you have an insert operation. Like what you can do is just append all these column values to the end of your file. If you have an update operation, you just find the location and you update it, the column values in place there. If you have a delete, you just look it up and you delete the values there. It's not so good for OLAP on the other hand, because like I said, you're only interested in a subset of the columns, and this model works on the basis of entire rows. So you're going to be wasting I/O reading column values that you're not going to need. And as we've assumed, I/O is expensive, so like that's not good. Yeah, so basically what we have is horizontal partitioning. So partitioning on the row level. Sorry. The Columnar model. I've explained it a bit. So instead of storing all the column values of a single row back to back, what you do is you store all the values of all the columns for all rows back to back. So in this case, if we have a row like this with the column values A0, B0, and C0, they would end up here, here, and here. And this is vertical partitioning. So instead of doing the horizontal partitioning on the row base, you do it on the notion of the columns. This is not very well suited for OLTP when you think about it, because if you're going to have to insert a record, you're going to have to insert these column values at various different locations, which are going to be spread out in memory. And if you have a big data set or a big file, it's going to be kind of inefficient. You're going to have a fragmented memory access pattern. You're going to have to like update all these values there or insert the values there. Computers don't really like fragmented memory access patterns, right? For OLAP, on the other hand, this is good because, like we've said, we're only interested in a subset of the columns. So if you're only going to want to read A or B, you're only going to read column A or B. Essentially, what you get is free projection pushdown, which is a fancy term for column pruning, which is just a fancy term for only reading the columns that you're interested in. Also, a nice thing about this is that since the values you're going to store back to back are from the same value domain, it presents nice compression opportunities. And you can do stuff like run length encoding, which I'll get into later. So let's compare the two models in the context of an OLAP query. Let's say you have a query that's interested in column A and column C, just those, and you would like to access it with the row-wise model. What you would end up with is this memory access pattern, which kind of sucks, right? It's very fragmented, and computers don't really like fragmented memory access patterns. Like even considering modern memory subsystems, you're not going to be able to, if your value is small enough, you're not going to be able to read just that value. Like if you're going to be reading from memory, you're always going to be reading at the granularity of cache lines, which is 64 bytes. And if you're going to be reading from disk, it's going to be an operating system sized page, which is 4 kilobytes. And if you're going to be reading from the network, it's going to be some other granularity. If we look at the Columnar model, on the other hand, we get this nice sequential memory access pattern. And it turns out that computers really like sequential memory access patterns. You can do stuff like cache prefetching or prefetching from disk. You're not going to be wasting I/O on reading column values that you're not going to need anyway. So, all good, right? Not really. Like if you want to do row reconstruction, like you still want to be able to get rows in the end, the Columnar model might not be as optimal as you'd like, because let's imagine you have a 100 gigabyte a data set and you have 10 columns and you want to reconstruct the row, part of a row consisting of the first, the third, and the last column. You're going to have to read the first 10 gigabytes to get the first value, and then the third 10 gigabytes, and then the last 10 gigabytes. It's going to be very all over the place, and you're going to lose the nice locality properties. And look, modern computers and modern memory subsystems are kind of built around making things fast because of locality and caching. So what's the answer? You probably have guessed it. It's the hybrid model. So in this case, you would store your row, your logical row like this, and it would end up here. So what we do is we apply both horizontal partitioning around the rows. So in this case, we do horizontal partitioning every 3 rows, and within those 3 rows, you do you apply the columnar model. This is used by Parquet and other columnar formats, such as RC, and basically it gives you the best of both worlds in the sense that you get the nice locality properties of the row-wise model and the nice I/O properties of the columnar model. So we finally get to Parquet. Quickly, it was initially an effort by Twitter and Cloudera. Open source storage format uses the hybrid model. In the scientific literature, this is referred to as PEX, or partitions attributes across model. It's widely used in the Spark and Hadoop ecosystem, and one of the primary formats used by Databricks customers. So what does a Parquet file look like? On disk, it's not actually a single file. The logical file is defined by a root directory, and this root directory contains one or multiple files directly, or it contains a subdirectory structure defined by a partitioning scheme, which I'll get into later. But you can end up with something like this. So how is data actually organized within such a Parquet file? Like I said, you have both horizontal partitioning and vertical partitioning. The horizontal partitions in Parquet are called row groups. You can have multiple row groups in a single file. And the default size for those is 128 megabytes. And within those row groups, you do your vertical partitioning, or you store your columns or your data in a columnar fashion in so-called column chunks. And within the column chunks, you store the actual data in so-called data pages. And the data pages have things like metadata, such as the minimum value, the maximum value, the number of values in that page, repetition levels, and definition levels, which I won't get into, but it's basically a means to reconstruct nested schemas. And you have your encoded values themselves. One thing to note is that you also have metadata at the row group level, but these are stored in the footer. And I'll get back to why that is nice to have all the metadata in one single location later. So how do you actually store your values? The Parquet specification features around 6 encoding schemes, but most of them are in the V2 spec, which, to the best of my knowledge, is not completely finished, or at least not really used in production yet. But someone might correct me on that later. But the main ones you're going to be concerned with for the V1 spec is plain encoding and dictionary encoding. So plain encoding is what it sounds like. It's plain. So if you have fixed width values, they're going to be stored back to back. So if you have integers, you're just going to store them back to back. If you have non-fixed width data, the length is prefixed to the data element to denote when you can stop reading. Where things get interesting is with hourly dictionary encoding, which is the combination which combines several techniques like run length encoding, bit packing, and dictionary compression. And it's based on the assumption that in your data you're going to have duplicate and repeated values. I think this is, when you think about it, it's a fairly a valid assumption, right? Just imagine you have a data set of 10 billion rows and you have a country column. There's only so many countries in the world, so you're going to be repeating those values, and they might actually, so you're going to have duplicate values. You might actually also be repeating those values. So a quick example of the country example that I just gave. If you have your uncompressed data like this, there's several values, and there's duplicates and there's repeated values. Let's say you have the United States. You see it's the last element as well. The Netherlands is repeated, and France has a duplicate somewhere else. So the first thing the Parquet encoder does when it tries to encode this data is to keep track of all the unique values that it encounters. And then you end up with a dictionary. So in this case, you have 4 unique values in your original data set, United States, France, Germany, and the Netherlands. And basically what this gives is, you could sort of conceptually see it as an array with the index being like the dictionary code, which you can use to encode your original data, which we've done in this example. So instead of storing the values explicitly, you reference the dictionary element. What it does then is it implies run length encoding, which is a technique whereby instead of storing repeated values explicitly, what you do is you store the repeated value and the number of times it's repeated. So in this case, the Netherlands is repeated 3 times, and the dictionary code 3 is repeated 3 times. So instead of storing that explicitly and wasting space on the repeated values, you store the value that's repeated 3 and the number of times it's repeated. The last thing that is done is bit packing, which is a nifty little technique whereby you only use the maximum number of bits you're going to need to store the actual values. So like I said, you could conceptually treat it as an array with the array index being the dictionary code. Like, you could store this in a 32-bit integer, for example. But if you look at this dictionary, it only has 4 unique values. And how many bits do you need to store the numbers 0, 1, 2, and 3 at max? It's going to be at max 2 bits, right? So why not just use 2 bits to store all these values instead of the full 32? I mean, you can see that if you have a relatively small dictionary, this can lead to some significant space savings. So finally, we can get to some optimizations. First thing to do is just accommodate for dictionary encoding. I mean, if you have smaller files, it means less I/O, and we've assumed that I/O is expensive, so your query is likely going to be faster. There's a thing to note here, though, that you only have a single dictionary per column chunk, which was the vertical partition in the horizontal partition, what is called a row group. So while Parquet is encoding your data, it's going to keep track of the dictionary, and it's going to reach a limit. There's a size limit to the dictionary. And if it's going to, so what happens if your dictionary gets too big? Parquet is going to fall back to plain. So your dictionary is filled up, and the rest of the data is just going to be encoded using the plain encoding format. And it's going to miss all the compression opportunities. And that's not good, because your file is going to get bigger. So what do you do to combat this? There's basically 2 things you can do, very easy things. You can increase the dictionary size. It's a configurable parameter. It's this Parquet conf, Parquet dictionary page size. The other thing you can do is just to decrease the row group size. This makes sense, right? Because if you decrease the row group size, you're going to decrease the number of rows, which means you're going to decrease the number of values in the column, which in turn increases the probability of those values, all the unique values in that subset fitting in the dictionary. So how do you actually inspect this, whether this has any effect? If you really want to get down to it, you can use Parquet tools, which can be found in the open source ParquetMR repo. You can just compile it and run it on Parquet files, and you can dump stuff like the actual data or metadata about the Parquet file. So in this case, I ran it on a file that I have, and it shows me that I have a row group 0 with a column ID, and within that column, I have all these data pages. In this case, it's not actually dictionary encoded. As you can see, there's VLE in the middle, and that's the value encoding, and it says plain. But that's because this is a primary index column, so all the values are unique, so it doesn't make any sense to store them, the dictionary encode them. So another thing you can do, or that Parquet allows for, is page compression on entire data pages. So you can outright compress entire data pages using a variety of compression schemes, such as Snappy or gzip or LZO. There's a Spark conf you can use to set this. But it only, of course, makes sense if the savings that you have on I/O by having a smaller file outweigh the cost of having to decompress the data. And it turns out that that actually is the case for lightweight compression schemes such as Snappy. I ran a simple benchmark here. Simple 10 gigabyte data set. I put it on S3 and then just do a Spark read Parquet collect on the entire thing. And when you have the data in the uncompressed form, it takes about like 14 seconds to read. And if you have the exact same data set compressed using Snappy, and it's 6 GB, the actual query, just reading the data, the exact same data takes around 8 or 9 seconds, which is quite a significant difference, right? It's practically always enabled by default, but it's still good to be aware of. So let's look at some more interesting optimization techniques. Let's say you have a simple query like this. So a select star from your table where the column X is greater than 5. So remember I talked about the min-max statistics in for the row groups that we have. They're all stored in the footer of the Parquet file. So if you, that's one of the first things Spark does, and Parquet does. When reading a Parquet file is you read the footer, and then you have all this metadata at your disposal. And what happens then is that you can reference this. You can leverage this metadata to do row group skipping. So let's say you have all this metadata for example, for these 3 row groups, and you have your predicate X is greater than 5. If you look at the min and max values of the first row group, you see that we have a min value of 0 and a max value of 9. So you basically, it's guaranteed that there's going to be a value that satisfies your predicate in that row group. Like there's at least one value that has the value 9, which means you're going to have to read the row group. But if we look at the third row group, we see that we have a min value of 1 and a max value of 4, which basically means that we do not have to read the row group because there's no way there's going to be a value in there that's going to satisfy our predicate. And as you might remember, the row groups can be 128 megabytes in size, so skipping 128 megabytes is a good thing. So yeah, you can enable this using this Spark config, which will tell Spark to push down the predicates that it receives into the Parquet reader. It's also practically always enabled by default, but still it's a good thing to be aware of. However, it doesn't always work. Like, it doesn't work well on unsorted data. If you have a large value range, so you have a very low minimum value and a very high maximum value, then the chances are that the predicate that you have is going to be for some value in the middle of that, right? So what can you do to combat that? One of the things you can do is to pre-sort your data on the predicate column, so you get more narrow min-max ranges. Another thing to be aware of is to always use typed predicates, so to match the predicate that you supply in Spark and the actual column type. So don't rely on any internal casting or conversions, because they unfortunately do not always get it right. So for example, use actual longs in your predicate if you have a long column, so do not use an integer in your predicate. So what about an equality predicate? Let's look at the same example that we had before, but then we do an x equals 5. So if you look at the metadata, for example, in the first case, we have the minimum value 0 and the maximum value 9. So is the value 5 in there? I mean, could be, right? Doesn't have to be. Could be all zeros and 1 9. It would still produce the same min-max statistics. So we're still going to have to read that row group. But one nice thing that Parquet has is a thing called dictionary filtering. So if you remember, the dictionary is a collection of all the unique values that you have in that column chunk. And it's stored in the beginning of the column chunk. So what you can do instead of reading the whole thing is you reference the dictionary. See, is there one value that is equal to 5 in there? And if there's not, you can, like with 100% guarantee, skip that row group, because there's not going to be a value that is dictionary encoded with a reference to the value 5. So that's good. We can do more skipping. I think this is a very cool feature. It can be enabled using the following Parquet config. Another thing that we can do is like a more high-level form of predicate pushdown, whereby you embed the predicates that you have into the actual directory structure of the file. This is very useful if you know the predicates of your workload beforehand. Like, let's say you always have a query, or you have a query that always has a predicate on the date column. What you can do is you can do a partition by on the date column of your data frame, and then what Parquet and Spark does is will generate this subdirectory structure for you. So you have these subdirectories within your logical Parquet directory with specific values for that column. And then all the files in that specific subdirectory will have those values for that column. So essentially what you're doing is you're translating predicate evaluation into just figuring out which files you should read. And this works well, like I said, if you know the predicates beforehand. But it can also be problematic. Like if your workload changes or if your predicates change, then this can work against you because you might end up with having to read more files than you would have if you had not applied this partitioning scheme. Which brings me to my next point, which is like sort of the root of all evil, basically, which is having many small files. So remember that for every file, you have to set up internal data structures, you have to instantiate reader objects, you have to fetch the file, and you have to parse it. Like that's a lot of overhead. And to demonstrate this, I ran another simple benchmark. So the same 10 gigabyte data set stored on S3, and you just read it in. Nothing special. But if you have the data set in 16 files, we see that it takes about 12.5 seconds to read the thing. And if we have the exact same data set in 1,024 files, we see that it suddenly takes almost 19 seconds. Like this is a significant difference. Like this is something everybody should be aware of. That if you have a lot of small files, this overhead can play a big part, have a significant contribution to your total query time. So what can you do to combat this? Well, basically there's manual compaction, right? You can just take your data frame and you can repartition it. You can do that in these ways. You can call repartition directly, which does a shuffle, and then you end up with files that are of the same size spread over the number of partitions that you provided as a parameter. Or you can use coalesce, which does pretty much the same thing, but it avoids the shuffle, which as a result, you might end up with files that are unequal in size, but it's still going to have the provided number of partitions. A thing to note with this problem is that you should always watch out for incremental workload output. Let's say you have an ETL job that runs every hour and appends data to a table. In Parquet, what this basically means is that you're going to be writing a new file. And you can imagine that if this runs every hour and you let it run for weeks and months, you might end up with thousands of or tens of thousands of small files. And as we've seen, that can be problematic if the files are small enough. That being said, the opposite is also true. Avoid having very few huge files. This is a story that a colleague of mine told me. They were debugging an issue with a customer whereby they were ingesting data per day. They had 250 gigabytes coming in per day, and they were trying to see what the best way was to compact that. So in one case, they would use 250 partitions, and in the other case, they would just dump the whole thing in one file. And they were seeing some weird performance performance issues there. So to debug this, they just did a simple query like a select count star on the entire thing. And for the data set in 250 partitions, this took about 5 minutes, which is kind of good. It's nothing strange. But then for the one huge partition, like guess how long this took? Like it should make sense that this is faster, right? Because you're avoiding having many files. It took over an hour to complete, which is crazy, right? If you think about it. So why is this? If you have a huge file, what else? Like if your Parquet file is huge, there's another thing that also becomes very huge, and that is the footer, because you're going to have lots of row groups. There's going to be lots of metadata that you're going to have to store. And it turns out that the footer processing is just not optimized for speed. So you have to be aware of this as well. But coming back to my original the original problem of having many small files, I mean, you can do manual repartitioning, right? You can just go to your data and just tell everybody, okay, do not touch it. I'm going to be repartitioning our data to solve this issue. I mean, ideally, we want to automate this process. But like I said, what about concurrent access? Like, are you just going to tell everybody, okay, stop touching the data? If you have many different teams in an organization, like this does not scale. You cannot tell everybody, okay, stop touching the data, we're going to be repartitioning now. Like, it doesn't work. Like, what you're going to need is some form of isolation of your operations. For example, you need asset transactionality, and that would be really nice to have. So is there anything for Spark and Parquet that we can use? I guess nobody sees this coming. There is Delta Lake, yay. So yeah, what is Delta Lake? It's an open source storage layer on top of Parquet in Spark. It provides you with asset transactions and stuff, and other cool stuff such as time travel. It does so by keeping track of a write-ahead log. And if you just store all the old files that you still have, there's a way to backtrack and then see the older versions of your table. It does other cool stuff, which you probably have heard about these last days. But what it does allow us to do, like, it gives you the tools to actually implement automatic compaction, because you're not going to have to worry about concurrent access, which is exactly what we did at Databricks, is implement this. So we implemented the optimize function, our SQL call, which does exactly that. It repartitions your data into more agreeable file sizes. But this can also be done automatically, right? We can just flip a flag and say repartition whenever it's deemed that these file sizes are not aligning or anymore, or not of agreeable sizes. There's additional stuff that we can do, since we have the write-ahead log, which is basically a collection of commits referencing Parquet files. We can store additional data there, right? We can store things like the min-max statistics there, which is exactly what we've done. And then we can do skipping based on the min-max of entire files, in addition to the row group skipping that's already there. And the cool thing about this is that these commits are stored in JSON files, but every 10 commits we create a Parquet file that stores the information in those 10 commits, which means we can read in this metadata using Spark, which means that it can grow very big and still be scalable. Yeah, so scalable metadata processing, because we're using Spark to read the data, but also read the metadata. So there's no additional metadata layer on top of it. It also allows us to do cool stuff like Z-ordering, which is basically a neat way in which you can cluster your data on multiple columns. I mean, you can do sorting on multiple columns anyway, right? But you'll end up with a major-minor sort, where you would first sort on the first column and then on the second. But the effect is that it would always bias the first column that you chose. So Z-ordering uses like space-filling curves to create narrow min-max values for multiple columns. So yeah, let's quickly look at what I've discussed today. So basically, we want to reduce I/O. And how do we do this? By reducing the size of the file, which can be done by using page compression in Parquet and to accommodate for the dictionary encoding that we have. We can avoid reading in irrelevant data. So we can do row group skipping based on the min-max values in at the row group level by reading the footer. And we can do dictionary filtering by evaluating the predicate on your dictionary instead of the whole row group. And we can leverage Parquet partitioning, so embedding the column values in your subdirectory structure. We've seen that we should reduce overhead, or at least keep this in mind, by avoiding having many small files, or as the example demonstrated, a couple of very big ones. And we briefly talked about Delta Lake, which is a layer on top of Parquet for Spark that allows us to implement stuff like auto optimization or auto repartitioning and compaction of your data set, and gives you additional skipping abilities by storing additional metadata in your so additional statistics on your data set in the write-ahead log, which then can be read using Spark, which is pretty cool. And we can do stuff like Z-ordering, which is also kind of nice. So yeah, that's all from me. Thank you for listening.
Thank you, Boudewijn. We got about 5 minutes. We got 2 mics on either side. Feel free to come forward and ask questions if you have any. Thank you.
There are.
Hi.
Hey.
Thank you for your talk. And you mentioned partition by, and this data frame write rate also has
Sorry, could you
bucket.
move a bit more closer to the...
Yeah, sure. You mentioned partition by for this data frame writer, but data frame writers also have bucket by. Can you explain what's the difference between partition by and bucket by? When would you recommend one over the other?
So partition by is more explicit in the sense that it just takes all the column values that it finds and it creates subdirectories for all those column values. So it makes sense if you have a limited set of column values, like for example in the case of dates. But it doesn't make sense if you have a whole bunch of, like if, I don't know, like you have tens of thousands or hundreds of thousands of values, you can end up with lots of small files. What bucketing does is it buckets, like it says, it buckets multiple files based on a hash of column values, so that you end up with a sort of a group of rows that have similar column values, but it's not based on these distinct column values. So I guess bucketing makes sense in the case that you have a lot of distinct column values, in which case a partition by would result in having like thousands or tens of thousands of subdirectories, which doesn't always is not as performant as it should be.
So I guess that Parquet does store also some metadata that this data is bucketed, so that Spark can then improve on reading or joining later.
Sorry, could you repeat?
So let's say I have my data frame, I say bucket by and write it, and then when I read it, is this information stored in Parquet so that I know, okay, this data is actually bucketed and it can improve things?
I don't believe it is. I think it's just like the physical layout is what determines the bucketing. I don't think there's any additional metadata, but it should increase performance by the fact that you're bucketing on specific subranges of the column values.
Okay, thank you.
No worries.
Okay, go ahead.
Yeah, first of all, thank you for a great talk. So my understanding is Z-order only comes to play when bucketing and partitioning is not working, right? Because it's for multiple columns. So, but can we say still like a Z-order is something like bucketing? And at this, the second question is like, and Z-order is only for like finding something like doing search, or it can also improve the join or it can also optimize the joins, like equi-joins, and can we compare that with the, at the same level as we can optimize the join on partitioning and the bucketing, or can you tell me something about that?
So your first question was...
Can you repeat the first question? Did you mean, does the ordering come into play?
Yeah. Z-order come into play when bucketing and partitioning is not working because it is for multiple columns, right? And
yes.
at the same time, can we say like it's bucketing and Z-order is something similar?
Yeah, I guess they're both means of clustering your data in a more efficient way, so you can then read it in a more efficient manner. So I guess, yeah. And I'm sorry, I forgot.
Yeah, the other question is like, is it going to improve the performance of the joins?
Oh, I see.
Yeah.
Yeah, I guess. Yeah, I guess any means of more efficiently reading in your data, which in turn means reading less data. That's basically what you're trying to do, right? Because even with Z-ordering, you're trying to max or to optimize the min and max values, which even when you're joining data on a specific column, then if you're going to be reading less data in this place and less data on the other side of the join, then yeah, your join is going to be.
Okay, we only have 30 seconds, so make your question really short. Thanks.
Okay, so thank you for your great talk. So my question is about the row skipping. So I understand that there is the metadata about min, max, and dict filtering to have this feature.
Yes.
And my question is about non-numerical data. If we have, for example, some text data, but is not duplicated so much, there is some metadata on Parquet to have optimized query on this way.
So in Parquet there is actually min-max on non-numerical data as well, so like strings and dates. But yeah, I mean min-max data is irrelevant of the. If you have your column, in which case you do not have many duplicated or repeated values, then you can still have these statistics, which could make sense. So yeah, I guess.
Yeah. So if I order for example, my data before writing it on this column, I will have the min-max on this non-numerical on the metadata. Okay. So
well, give a hand to Boudewijn again for a wonderful talk about the guts of Parquet. Thanks a lot.